Okay. So anyway, thank you for your patience and thank you for attending our event. Uh, and this will be the fifth webinar of our East 101 webinar series. If you like our content, we hope you'll help us by spreading the word. So for those of you who might be new to us, we are a specialty consulting company focused on providing advanced process engineering and flow assurance consultancy services to the oil and gas industry through process simulation technology. Our track record, we were founded in 2003 by engineer Rafil Elyas, our speaker today, and we have offices all over the world, but we are based in Kuala Lumpur. Our track record includes projects which cover transient or dynamic simulation-based engineering services, so there'd be design and troubleshooting, and flow assurance analyses, operational assistance, especially OTS, operational training simulations, which really help to make sure that your operations are safe and cost effective, and process simulation training for steady state dynamic simulation software. Right. So these are some of our clients. For any inquiries about our services, please contact either myself, Zihong, or my colleague Avinash at the numbers and email addresses shown. We'll copy this information and leave it in the chat box for your reference. More information is available on our website www.east101.com. So what is the East 101 webinar series? Through our webinar series, we hope to cover a wide range of topics, from upstream process design to downstream and refining, monitoring, surveillance, as well as analytics and AI. The webinar is scheduled to take place every other Wednesday from 4 to 5 p.m. Malaysian time. Our next talk in 2 weeks' time is about introduction to PipeNet for liquid pressure surge analysis. And the speaker will be Mr. Kevin Chu, one of our best process engineers at East 101, with 3 years experience in the industry. Kindly mark your calendars for the 26th of August 2020, 4 to 5 p.m. Malaysian time. Before I introduce today's speaker and topic, here are some housekeeping items to think about. We will have one speaker this evening, speaking for about an hour, followed by a Q&A session. We kindly request everyone to stay muted to avoid interference. If you have any questions throughout the presentation, please put them in the chat box, and they will be addressed for the presenter at the end of the video. If at any time you experience any difficulties with the connection, feel free to reconnect to the room using the same. If you miss anything, the recording of this webinar will be available within a week on our webpage under the webinar events. Now, today's speaker is engineer Elyas, and he'll be speaking on the topic of full blowdown distributed model approach. Since graduating from Syracuse University with a bachelor's degree in chemical engineering, engineer Rafil has accumulated over 30 years of experience in the industry. He has also over 15 years of formal training experience since he started lecturing for John Campbell Group, and currently runs training courses which we brand as East 101 University. He is currently an industrial advisor an adjunct lecturer for several universities in Malaysia, as well as chartered engineer and fellow of the ICANN. Without further ado, allow me to invite Engineer Elyas to share the expertise and knowledge. Rafil?
So you should be able to see this screen where we have the East 101 University logo. So we'll give a free East 101 t-shirt to anyone who can tell us what the meaning of that, of the motto is. The East 101 motto, Debriatus ex fonte siente. So type your answer in the chat, and the first three who submit your translation or what that meaning is will get a free East on the One t-shirt. So put your name and your email address, and we'll contact you for your details. So let's just start this. I'll be talking about, as Young's introduced earlier, a distributed model approach for coal blowdown analyses, also referred to as a coal depressuring. Yeah. So let's get started. So I'll be talking about the following today. This will be the agenda for this presentation. I'll talk about the typical scope for a coal blowdown analysis. In this particular case, it's for an offshore facility. I'll run through the problem definition, what the issue is. Then I'll talk about how this is generally modeled or represented from a traditional basis. Yeah. So if those of you who might be coming from the HISIS universe, there's probably a particular way that you'd handle blowdown analyses using the built-in blowdown utility. So I'll talk about that very briefly, traditional analysis. And I'll go into the requirement of having something a bit more rigorous with more granularity with regards to temperature identification of temperature profiles, detailed temperature profiles using what we developed, which is a distributed model. And then we'll go into the question and answer after this. Yeah. Okay, so let's start. If for any reason you drop out, or if the sound gets choppy or something like that, please just let us know in the chat box. We've got some staff that are monitoring that. So the first thing I like to do is to talk about typical scope of blowdown analysis in an offshore facility. Yeah, because this is applicable for this analysis that we're doing. This example that we're doing over here is for an offshore facility. So why do we need to do these coal blowdown analyses? Coal blowdown analysis essentially, in summary, is essentially taking a look at a system, a closed volume or a closed system. In this particular case, we're looking at like a fuel gas import system, which has been shut down, and there's essentially some trapped gas in that system at a high pressure. And what we'd like to do is we'd like to then blow that down, blow that system down, and then take a look at the temperature profile across the system. So the objective for this is to essentially determine the minimum metal temperature for all the piping and the equipment within the system. When this is done at the design stage, this temperature would be generally used as the minimum metal design temperature. If this were an existing system, and we've done some of these analyses for existing systems, this analysis would be used to determine if a particular blowdown strategy might result in a temperature which may breach the minimum metal temperature. So this would be an existing system. Perhaps you've got some infill drilling, and you're bringing in like a new hydrocarbon source into your facility. So you'd like to take a look at if there's going to be any potential issues if we bring this new hydrocarbon source with new hydraulics and new compositions. Yeah. So we've seen these analyses done. We've done it for both existing facilities and for grassroots facilities, new facilities. Okay, so In this schematic, I'm essentially presenting your typical setup for an offshore hydrocarbon processing facility, hydrocarbon production facility. So the area that we're interested in, if you take a look over here, we've, let me see if I can get my laser pointer on. Okay, we started off at the wellhead and go down to production separator. Now these are pretty much, these two areas are going to see a lot of high pressures. And as you go further down, your gas compression system, this green section over here, you'll typically see high pressures as well. Down here, you start seeing following the liquid train. So this is the purple is essentially the oil train, and the blue section would be the produced water train. So for this particular analysis, the cold blowdown would be applicable for these sections in red, the high pressure sections, pipeline wellhead sections, risers, and the production separator. Okay. So let's take a look at the problem that we have here. Now, this particular system that we're looking at is for a floating processing, storage, and offloading, FPSO, fuel gas import section. If you're not familiar with an FPSO, this is roughly the configuration of an FPSO. You notice that these days hydrocarbon resources are essentially being exploited from deeper and deeper water depths. So it's no longer feasible in some cases to have like a fixed structures. We're looking at water depths of maybe about 1 to 1.5 to 2 kilometers deep. Yeah, there are other obviously economic reasons for implementing an FPSO as opposed to a fixed platform. So in this particular case, this is the layout, roughly a layout on an FPSO, and this is rather. This is just like a very simple sketch. Typically for a system like this, you've essentially got subsea wells, and they're tying into like a pipeline end manifold on the seabed, PLEM. And then there's typically a flexible riser that transmits the hydrocarbons up to the FPSO. Now, the FPSO in this particular example has something called a turret. And I'm not going to get into this because I know just enough about marine architecture and marine vessels to be dangerous. So this turret essentially is a very complex device. What it does is it allows the pipes or the hydrocarbons to be transmitted onto this processing facility, and it essentially allows for movement of the vessel. Yeah, so it's a fairly complex structure. And there are companies, the FPSO companies, generally, that's essentially their major, I guess, proprietary bit of information on how these turrets and swivels within the turrets are designed. Yeah. So within the turret is a device called a swivel, and this essentially is an interface, acts as an interface between the hydrocarbons coming in to the topside. So again, I know just enough about the mechanical aspects of this to be dangerous. So I'm sure there are people from the FPSO organizations that are better versed in the workings of these turrets and swivels. Okay, so the problem is as follows. So I've taken that picture and kind of reduced it to this schematic. For this particular system, fuel gas is imported from another facility. Yeah. So the fuel gas is essentially piped in through an infield pipeline, and it's one of the lines, many lines that come through the swivel. So this section, this area here is essentially the fuel gas, essentially the fuel gas section, consists of the fuel gas riser. We've got a shutdown valve here that goes into the swivel. From the swivel, then it goes into the fuel gas heater, metering, and then to the consumers. So this is the section that we're interested in. We're looking at the volume between the SDV 001 and SDV 002. So the starting point for this is This system is in essentially constructed in a cold climate. So the minimum ambient temperature is -8 degrees Celsius. So this obviously is not in the South China Sea. And the settle-out positions, settle-out conditions over here is essentially about 150 bar gauge. And it's desired to depressurize the system to about 6.9 bar gauge. So the starting point is essentially based on an isochoric constant volume settle-out. And this is the initial state over here. So this is the problem that we're looking at. Now, if we take a look at the swivel section here, as I've shown you, the swivel essentially consists of several types of toroidal structures. And if I just simplify this, for all intents and purposes, we can look at the swivel as a structure which has different wall thicknesses or metal thicknesses, yeah? So we're taking a look at all the various segments within this swivel. So if you look at it, it's kind of like several donuts or toruses kind of stacked in a structure. Yeah. So we have like all this, the various structures essentially yield different wall thicknesses. So the issue that we have over here is the swivel design temperature is -30 degrees Celsius. Upstream of the swivel at the heat exchanger and the fuel gas metering system, excuse me, the design temperature is much lower. It's about -60 degrees C. So it's a low temperature design. Yeah. Excuse me. So let's go to the next slide. Let's take a look at how this would be done traditionally. So I'm going to bet, looking at the list of the attendees, I'd say about 80 to 90% of the people attending this have used a lumped model, or the if you're using HYSYS way back then, it's the dynamic depressuring model, yeah. Or if you're using HYSYM, if you're old enough to remember HYSYM, they had like a built-in sort of pseudo steady state model. So how would we typically model this? Well, using the lump model, we take a look at all of these volumes, all the metal weight, all of the metal area, and we'd lump that in a single vessel. Yeah. So we take a look at all the equivalent volumes. We'd lump that as a volume. We take a look at how much metal there was to come up with a total metal weight. And then we essentially identify a thickness, a wall thickness we'll do it based on some conservative wall thickness. So you might choose like the thinnest wall or something. So what you get up, what you end up is after you lump all of these things is you're essentially going to have like a very, very long separator with the equivalent metal and surface area for heat transfer as you get in this system. Yeah. So this is traditionally how you do it. And like I said, if you're using, if you started your career in the 80s or 90s and you're using HYSYM, they would essentially do some kind of like a pseudo steady state step representation. Later, when they came up with HYSYS, they started using the dynamic engine with all the integration to essentially solve for that. But until I think about 4 or 5 years ago, these models were just based on a single volume. Yeah. And based on this analysis, the results were as follows. Starting at an initial temperature of -8 degrees Celsius, if you were to do a depressuring on here for about, where you're taking it from about 160 bar to about 6.9 bar, we find a minimum fluid, hydrocarbon fluid inventory temperature of about -41 degrees Celsius. And it yields a minimum wall temperature of about -23 degrees Celsius. So if I'm designing this facility, I'd be a bit concerned because I really want to know where those low temperatures are going to be. Second, because I'm kind of lumping and I'm averaging volumes and things like that, these temperatures are going to be kind of, they might not really be indicative of the actual temperatures that I might encounter. So this is the issue. With this lump model, I don't know spatially where this low temperature is going to occur, one. And two, I'm not sure that I can trust or feel confident of the number that gets calculated because of all of this averaging. So that's a problem that I have. Yeah. So I can't see the cold spots. I can't get the accurate inner wall temperature. How am I going to identify where the temperature might be lower than the average temperature predicted? Yeah. And I'd like to know also across my system, is every point spatially going to be above, every temperature point spatially across the system, is it going to be above the minimum design temperature? Okay, so now here comes the distributed model. So this was built quite some time ago, but we still use this for our analyses. Yeah. And what we're looking at is we're looking at a transient analysis based on a distributed model. What we mean by this is we essentially account for every piece of equipment, the piping inventory, pressure drop, and heat transfer. Next slide, I'll get into a bit more detail about that. We've also done some rigorous wall modeling to better account for the thermal gradient across the wall. If you take a look at most of your simulators, particularly HYSYS, Unisim, Symmetry, VMGSim, you might be able to put in like wall layers, but you might not be able to get like a very detailed temperature gradient across your wall. Yeah, you can put in insulation, different insulation across your wall. Another thing is, yeah, we also did a check to take a look at the sizing of the blowdown valve in this particular case, but I won't be talking about that in this analysis. Okay, so for this strategy, just to give you a bit of background, in this case we used HYSYS as the main simulation environment. I'm not sure if there are many HYSYS or Unisim or Petrosim. They're all coming essentially from a very similar source code. But this family of products is essentially built to be extensible and programmable, meaning you can bolt in. I think if you've been to some of my previous webinars or been into my previous trainings, one of the things I talk about is customization of this environment, the HYSYS environment, or the HYSYS family environments. It's highly customizable. You can add your own Visual Basic Code, or you can create your own applications using any of the Microsoft Visual Studio tools, or even Fortran. You can wrap up the your subroutines as dynamic link libraries, DLLs, and you can call them within HYSYS. So in this case, we used HYSYS as a basic framework, and we used HYSYS Dynamics. So we used some of the native HYSYS objects, but what we did was we reprogrammed those objects. So we used our own custom heat transfer equations. In some cases, the heat transfer granularity at that point in time was not very rigorous. So we wanted to take a look at heat transfer between phases, and also heat transfer, I guess, from a convection perspective, both free and forced convection. I think some of at that point in time, the built-in heat transfer model, particularly for some of the vessels or some of the other objects, did not take into account forced convection. Yeah. In addition to that, we wanted to take a look at the heat transfer across the wall. If you just use like one wall section, you'll essentially get a linear heat transfer profile, temperature versus like a wall thickness. In this case, we wanted a bit more resolution because we felt that that would also give us a bit more confidence with regards to the temperature prediction on the inner walls. That said, nowadays, most simulators have built-in distributed blowdown models. So I know that Aspen Tech had acquired the Imperial College code. I think it's called Blowdown or something. And they've bolted that into HYSYS. I know the competitors have also done something similar to that. So they have all of these heat transfer models. I don't think they have a finite element models though. So that said, we still prefer to use our own model for this, mainly because I have access to all the, I can see all my equations, and I feel confident when I can see my own equations. So we tend to use our own code for this particular type of analysis. Okay, so this is kind of what it looks like. So this is just a bit of a snapshot. I'm not going to go into much of the code, but as you can see, we're using HYSYS objects. So we're using HYSYS vessels, HYSYS pipe objects to represent pressure drops, vessels for us to bolt on some of the heat transfer equations. If you take a look at the inside the heat transfer, inside these vessels, we're using like a spreadsheet in this particular case to do some of the rigorous heat transfer coefficient calculations. So in this particular case, we look at free and forced convection. That's where we're calculating like a Reynolds number, Prandtl numbers, Grashof numbers. Yeah, for this, yeah. So it's kind of getting a bit more granularity on that. Again, we in this particular case, we really needed to get as much resolution as we could on the temperatures. Okay, so if we take a look at the case now, what we've done is after we built the model, which is the hard part, and after we've kind of tuned it, after we've tuned the model, we've done stability checks. Then what we did was we essentially took a look at the system that we had here from this particular FPSO, and we were monitoring. The first thing that we did was we wanted to take a look at the temperature profile as we came from the riser all the way to the consumer. So the battery limits were at essentially these shutdown valves, the isolation valves. So we've numbered all of these points, 0.1 to 0.8. And this is what it looks like on the graph. So this graph isn't from HYSYS. It was, again, it was post-processed. We collected all the information from all the strip charts in HYSYS, and then we bolted that into a spreadsheet, and now we put in like a bit of an animation tool so we can demonstrate this to the customer. So you can see all the sections over here, section 1 all the way up to section 8. Bear in mind that over here on the swivel section, I've got like a design temperature minus 30. Everything beyond that's a temperature of 60, minus 60. So I'm plotting two things here. Again, I'm starting from an isochoric settle out. I'm settling out at constant volume, meaning like I'm simulating like I've got this in the system isolated, and I'm allowing the inventory, the hydrocarbon inventory, to come into equilibrium with the ambient temperature of minus 8 degrees Celsius. So I'm starting at minus 8. So the red line is the fluid temperature, and the blue line is the inner wall temperature. Yeah. So I'm going to go ahead and start this if I can. Okay, so I'm starting the sim. You can see, so I'm blowing down from 160 bar gauge down to about 6.9 bar gauge. And you can see the fluid temperature start to drop as you're starting seeing this, the expansion of this fuel gas. And you're seeing also the Joule-Thomson effect as this goes across the system from 0.1 to 0.8. Notice the blue line over here. We're not seeing too much of a drop in temperature because this blue line is essentially the inner wall temperature. So the blue line still has a lot of heat in there. So it's essentially still have this as a heat reservoir. Yeah. So if I let this run and I compare against what I saw before, based on the lumped analysis, it predicted like an inner wall temperature of about minus 23 degrees Celsius and an inventory temperature of about like minus 40. So you can actually see it coming pretty close. But in this particular analysis, I can actually see where it's hitting those temperatures. And from this drawing, I can see that the low temperature areas that I'm hitting are generally upstream of the swivel. Where the upstream of the swivel, my design temperatures are minus 60 degrees Celsius. Yeah. So I'm based on this, I have some confidence. I mean, I can pinpoint exactly where my cold spots are going to be. So I'm interested in this blue line, because this blue line over here is my inner wall temperature. And you can see I'm around the swivel area. I've got like more than like, I've got like a fairly large approach to my design temperature. So I'm doing okay. Yeah. And as I start getting to the cold spot over here, where it's, my temperature is about minus 20 something, by then my design temperature is 26. So looking at this analysis, it gives me some confidence that my system is going to be protected, since I've got these two various, these design temperatures. So that's one part of the problem solved. Another thing I'd like to do is, again, because we weren't sure where we were going to see these temperatures, we also did a, initially, we see they're not really occurring over here. We wanted to, over here, as in the swivel, we just wanted to get an idea of what kind of temperatures we'd see in the swivel in terms of the wall, based on the wall, swivel wall, yeah? So what we did was we built a rigorous wall model for segment 4, which is like the thinnest slice of wall. And we wanted to see how low the temperature would go, and what would its response be to the blowdown. So what I have over here to the on the left-hand side, this is my fluid, hydrocarbon fluid. And on the right-hand side, this area here is my ambient section, yeah? And the ambient temperature is a minus 8 degrees C. So for this analysis, I'm going to start the blowdown again. And again, for this, I'm just monitoring the metal temperature, yeah? So this is, this analysis essentially was done with the previous axial temperature profile calculation. So let's take a look at what happens when we blow this down. So you can see the inner wall temperature starts to drop quickly, but you can see that you know, there's still quite a bit of heat capacitance in the wall. So it takes a while for the rest of the wall to see this. So if you had a temperature gun and you're aiming it outside, you'd still see about minus 8. Yeah. Now we can see that the temperature of the fluid is starting to affect the outer wall temperature. And you'll see something interesting as well. We also take into account the heat transfer from the ambient. So this inner wall temperature also starts to go up a little as we start absorbing more heat from the ambient, from the outside. Yeah. So you can actually see the temperature go down, and then it starts to climb back up again as the system kind of re-equilibrates. So what I get from this is I get more of a confident, I get more of a confident feeling for what's going to happen for the response of my system. And I could have done it for any of the wall sections over here. So again, this wall section here is not something that's built into the simulator. So that was based on a finite element piece of code that we wrote and bolted into the HYSYS framework. So that was a nice piece of code that we put in for that. And again, it's a highly, I'm not plugging HYSYS because they're not paying me for any advertising, but I think the original team did like a really nice job when they made it programmable and extensible. So it opens a door for a lot of customization like this. Okay, so just to summarize, we'll go back to the results and see where we had. So this is a plot of the minimum observed temperatures that we see from the axial profile, the spatial profile. And we can notice that the low temperature sections are appearing over here, the heater and upstream of that. And this is our lump model result. So in this case, we don't have any spatial information. So what this does is it essentially gives me some more confidence, because it shows that the distributed model shows that we don't have any minimum design temperature breaching during the cold blowdown analysis, during this blowdown event. Yeah. So based on this, what we can conclude is, well, this kind of analysis is giving us a lot more granularity on the system, the temperature and the thermal response of the piping and equipment. So we can be sure that whatever design temperature that we select and whatever blowdown strategy that we select for this should be safe. Yeah, so we make sure that we don't see any of the temperatures falling below the design temperature, leading to potential like a metal embrittlement. Using this analysis, also we have the opportunity to use low temperature material where we really need to use a low temperature material. So we can essentially save on capex when we have visibility on these these cold spots. Yeah. And obviously, we improve the reliability for this system, because when we're performing our blowdowns, we can be sure where these cold spots are going to occur. So in a nutshell, that's pretty much what we've done for this type of analysis. If you'd like some more information, you can just shoot a message over to Zihong or Avinash, sales@east101.com. And now what I'll do is I'll open this up for Q&A. I think the format is for people to type in your questions into the chat box, and I'll do my best to answer them. Okay, so I think I'm supposed to hand this back over to Zihong. I'm gonna just give control back to him. Okay. Zihong, do you have control?
Yes.
Okay.
Thank you, Rafil. Thank you, Engineer Rafil, for insightful and entertaining session. Well, one last item before the Q&A. Rafil, you mentioned that the first person, I suppose, who translated the motto from East 101 University gets a prize, right?
That's right. I guess we're given the first three correct answers to East 101 University motto. Firstly, I need to give you a disclaimer. So East 101 University is just as it's just as recognized as Trump University. Like, it doesn't really exist. So it's just like a little brandy thing. And the logo is something which I essentially stole from my old university. So they're not using it anymore. Syracuse doesn't use that anymore. So they've modernized. So I'm still using those kind of like
So
yeah.
Our first response to that is from Miss Nur Hidayah, who says, intoxicated from the fountain of knowledge. And she says she got that from Google Translate. Is that
Okay.
allowed?
Well, that's fine. I don't expect anyone here to have like a working knowledge of dead languages like Latin. So yes, that was it's actually the university. It's a Syracuse University logo, and I don't know if anyone here is familiar with Syracuse University, but we were, I think, for 5 to 10 years straight in the Princeton Review #1 party school in the United States. And I think back in the 1980s, you'd always see some guy from Syracuse University on MTV Spring Break, fairly intoxicated on the Florida beach. So I figured I'd take that, but in this case, would be intoxicated on knowledge rather than what the kids used to drink back in the 80s. So yes, that is correct.
Congratulations, Miss Nur Hidayah. Our second response from Iza from WESB, and they're saying intoxicated or drunk from the fountain of knowledge, which is the same, pretty much the same answer. Congratulations,
That's
Iza.
right.
Sulaiman, I'm not sure, I can't see the full name here. Says scientific knowledge based on demonstrable and reproducible data. That's just one word in the motto, right?
Sorry, could you please repeat that?
We have one response that says scientific colon knowledge based on demonstrable and reproducible data.
No, there's no drinking or intoxication involved. Sorry, we can't accept that.
We will not accept that, unfortunately. So we have two correct answers so far, and Rafil has said that the first three get a prize. So, in, uh, well, meanwhile, shall we move on to the technical questions?
Yep, let's do that.
Okay. Uh, in case anyone is attending who did not register, I'm seeing Isa as a guest account. If you did not register personally for the webinar, please give us your contact details so that we can contact you. Give you.
Yeah, Xiong, you're kind of breaking up. Your voice is kind of choppy on
Really?
this. Yeah.
I'm,
So
I'm speaking. No. Okay. I'll speak slower. Would that help?
no, it has nothing to do with the way you're speaking. It's an internet thing. There's some lag and there's some choppiness. So okay. Yeah, so I guess if what I'd recommend is for everyone to please register, particularly if you'd like to get one of the t-shirts, make sure you send us your email address so we know who to send this to.
So
Okay.
our contact information would be sales. You can just tell us that you answer the question in the webinar and we'll get back to you.
Okay.
All right. So our first technical question from Zulfan Adi Putra, who asks, was the ambient reference temperature used the same in every point, 1 to 8? I believe that was referring to the wall analysis, because he explains that they were expecting that the inner wall temperature touching the bulk of the fluid would have the same trend as the bulk fluid temperature. And they would like to know what happens at point 4.
Point 4.
It was the
What's in
wall.
the heater? Point 4 in terms of the spatial. Hold on, let me just. Every point. Yeah, sorry, it's point 1 to point 8. So the question is, the ambient reference temperature was used the same at every point. Yes, it was used. So the entire facility over here was exposed, is assumed to be exposed to the same ambient temperature. I was expecting that the inner wall temperature, it's touching the bulk of the fluid, would have the same temperature as a bulk fluid temperature. So yes, initially at the start of the simulation, let's see if I can get a picture of it. Okay, so at the start of the simulation, everything is settled at about -8 degrees Celsius. Yeah. At point 4, that's actually heat exchanger. So there's a lot of metal there. So what's happening is, let's say if this is the metal and if this is the fluid, initially they are both at the same temperature. Yeah, so they are going at the same temperature. Now what happens is, when you start blowing the system down, your fluid starts to move and you start to get an expansion of the fluid. And that causes, you essentially have your Joule-Thomson effect. Your fluid is expanding and it's being blown down. So it's being removed from your system. So this fluid temperature is starting to reduce. Your wall temperature will not reduce immediately. It's going to take a while for the wall temperature to start to come down because the wall's got a lot of heat already. Yeah, so your wall is kind of like a thermal reservoir. So when you start the blowdown, let's see if I can see here, point 4. Yeah, so at point 4, you can see that the metal temperature is essentially higher, a lot higher than the fluid temperature, because in this particular section here, there's a lot of metal. Yeah, and that metal acted as a thermal reservoir. So this simulation was just run for a few minutes. It was not run all the way till the end to have to show equilibrium. So we just stopped it. We just essentially stopped it at some point. Yeah. So based on the system, on the analysis that we did, this is what we see. So that temperature from the metal will take a while to come down, and it's still receiving. Bear in mind, from the wall temperature, you can see that it's still receiving heat from the outside. Yeah, so we don't expect that temperature to drop too low. Yeah. So I hope I answered your question there. Yes. So point 4, it's not a running heater, but the heater is shut down, but it still has a lot of there's a lot of metal associated with it, so it's acting like a reservoir. Yeah. Okay. I hope I answered that question. Next question. Right. Yep.
Thank you, Zulfan, for the question, and thanks, Rafil, for the answer. Next question from Pat Broderick. Rafil, did you try to run this particular problem through HYSYS Blowdown for comparison?
Good question. When Blowdown just came out, it didn't really have all the structure. In fact, I've to this day I've not really used HYSYS Blowdown or the Unisim equivalent. So the short answer is no, I have not compared it against that, and I've not compared it against any experimental data. The confidence that I have in that is based on the fact that I've got the heat transfer mechanisms, which I believe will provide the resolution and granularity. We haven't had the luxury of being able to compare this with any experimental results. And I haven't compared it with Blowdown, though I think if we probably get some interns, we might have them do a quick run. Because I think now, the current state of Blowdown now, they have enough structure to allow us to replicate what we had. When Aspen just acquired and bolted in the Blowdown software in the early years, they didn't incorporate all the structure that we need to have the full model to replicate this kind of a detail. But I think now they may have. So now it might be worth doing a comparison between that in Blowdown as well as Unisim's EO, the EO equation-oriented blowdown system. So, yep, we'll probably give that a try, Pat.
All right, that sounds very interesting, Rafil. Thank you for that insight. Our next comment from Khalid Sharma. I can't see the full name, I'm sorry. Khalid, Khalid says, could you kindly show us a demonstration of the work done on HYSYS?
Not at this point. I have the results. I don't have a license at this point in time because the license is currently being consumed by our team who are doing paid work. So unfortunately, I can't give you like a demo for this online like right now at this point in time. So yeah, apologize for that. But if you've got any other questions as to how we can how we've actually used this model, I can give you that. I can talk about that. But yeah, I don't have a working license yet. I've got like, and also as you get older and more in the management in your company, you tend to get left with the cheapest and slowest machines. So I don't have that on now. But you know, if you some point in time, if we're given some training, if you attend like one of our training courses, and remind me to show that, yeah, I could probably once if I've got like a HYSYS license, I'm doing some training. Absolutely, wouldn't mind just showing you how it works.
All right, Khalid, please drop us a line and let us know if you're interested in our training. The next comment from Victoria Bernard, again, I can't see the full name. Victoria says, I just want to make sure that I didn't mislook the information. Is the final pressure 6.9 bar gauge so shown in your slide for cold blowdown?
Yes, so we're going from 160 bar gauge to 6.9 bar gauge. That's correct. Those numbers are that number is correct.
Okay. Thank you, Victoria. Thank you, Rafil. Ayman Ayadi or Ayman Ayadi asks, as the model has been run for a case when, sorry, has the model been run for a case where an insulation has been placed, especially when we have a low temperature personal protection that can be placed in system portion that can be reached by personnel? I'm not quite sure I understand, but it seems like the keywords would be has the model been run for Ayman, just rejoin us. Welcome back, Ayman. So we are trying to understand your question. Has the model been run for a case when an insulation has been placed, especially when we have a low temperature personnel protection, which can be placed in system portion that can be reached by personnel?
Yeah. So I think I know. Let me just take that. We have, in this case, modeled systems with insulation. So essentially, that's just another layer on the outside. Yeah. So in this example, we did not have any insulation modeled for this particular system, but we have model systems with insulation, and all that introduces is another layer to be added to the heat transfer calculation. In our case, again, that's why in our case it's we like having this system because we can add on. We write when you write your own equations, you can do anything you want. You're not reliant on any limitations of your software. And that said, also the HYSYS environment allows you to program the existing tools, so you can add on anything that you want. So yes, we have run it with insulation in place. Whether all we need is essentially the conductivity of that insulation and the thickness. Yeah? So it just treats it as another layer with a different conductivity.
Thank you, Rafil. The next comment from Pat, not a question, but love the animation effect. Great to visualize the temperature profile throughout the system versus time, keeping the customer satisfied. Thank you very much, Pat.
Thanks, Pat.
So if anybody would like to ask any further questions, please type it up in chat and we'll be happy to answer. Oh, Yap Min Yi says, HYSYS Imperial College is a good tool for cold blowdown, recognized to determine wall temperature for distributed models. Any other specific applications besides the swivel that we need to apply FEM analysis?
Okay, well, thank you, Minyi. In this particular example, we were applying it for the swivel analysis just because it was the lowest temperature. It was the lowest temperature that we had. The lowest, sorry, it was the highest design temperature, minus 30 degrees Celsius. So we wanted to get some additional granularity or resolution around that. Yeah. So we would apply the wall model to whichever section where we wanted to get additional granularity on the temperature response. So that could be any kind of equipment or any kind of piping wall, where you require that kind of detail. That's when we would apply that finite element method. Yeah. So it really depends on the requirement.
Okay, thank you, Mini. Thank you, Rafil. Victoria is following up on the previous question regarding the final pressure of 6.9 bar gauge. They say, Victoria says, as I understand based on API, it is common that the final pressure is 6.9 bar gauge for fire case. Why is it 6.9 bar gauge for full case as well?
That's a good question. At this point in time, we just arbitrarily stopped the simulation, and I just wanted to pick something. I didn't want to just let it. We could have let it go all the way down. We could have blown it down all the way to atmospheric, but in this particular example, I just chose that that particular pressure to stop the sim. And again, it's just like you probably pulled that number from a fire case. Most of the cold temperature effects we were seeing were happening at much way before that temperature. At that temperature, about 6.9, the temperatures, everything started equilibrating. So it was just, in our case, it was just done to save time, so we don't run it all the way down to a couple of bar, because there wasn't really much interesting features that we're getting from the profile. Yeah.
Thank you, Rafil. Muhammad Hamza Hazri asks, what's the difference in using Olga versus HISIS for this blowdown run?
What's the difference in using Olga and HISIS? I guess it depends if you've got $1 million to lease software or 20 grand. I guess I've seen people doing blowdowns in Olga as well. What's the difference? Well, I guess one, if you're an engineering company and you want to do a blowdown analysis, I don't think you just get Olga just for that, unless it's for a particular pipeline blowdown, and you're going to use it for some additional flow assurance analysis, just from a cost benefit perspective. It's an awful lot of money to spend if you're just going to do like a blowdown on like a section like we're working with now, which is piping and not really pipeline. So if I was doing like a pipeline, like large pipelines, large undulating pipelines, networks, and I was blowing down the network or something like that, I might consider using Olga. Yeah, I might consider using Olga for that. So the reason we didn't HISIS is primarily because it was for piping section. So in terms of the difference, Olga actually has some rigorous wall models, and it's got femtherm, which is a finite element tool that you can use for rigorous heat transfer across walls and wells and things like that. So it's got a lot of built-in stuff that you could use if you wanted to use that particular framework. Yeah. So in terms of computation, HISIS off the shelf may not have the same kind of rigor as what we had used for this. Yeah. So in a nutshell, that's pretty much it. You'd have some similarities, and my main thing would probably be cost.
Okay, thank you, Rafil. And Khaled Shamam asks, how did we choose the time for the blowdown analysis? Was it 15 minutes or something else?
Okay, well, this wasn't, I think someone's mentioned correctly, I think Victoria mentioned, this is a cold blowdown, so we weren't looking at the fire case. So that 15 minutes or blowdown to 6.9, that I shouldn't have displayed that number here, because it wasn't really, it was just done as, because I just wanted to choose some end state for the simulation. I didn't want to bother waiting for it to go all the way down to atmospheric. So the blowdown time, in this case, it was there's no restriction on the blowdown, excuse me, time for this implemented. So for this case, I can't remember how long it was. I think it was, yeah, at the top of my head, I don't think it was 15 minutes. The analysis that we're looking at is happening at a time scale less than 15 minutes. As soon as you blow down this sudden drop in temperature, we're seeing that happening in less than 15 minutes of the simulation. So I'm not too concerned about the time for this because the blowdown device was already selected, so it blows down, and that's already been sized and everything. So in this case, we were more concerned about taking a look at the minimum temperature rather than the blowdown time. And again, because it's not a fire case, fire, you have that 15 minutes. That 15 minutes is essentially taking into account your material or metal failure, or how long it takes to clear the area. That's why you have the API 521 15-minute requirement for fire case. In this case, for coal blowdown, we weren't looking at time as a factor. That said, this phenomena, the lowest temperature that we observed, happened before 15 minutes. So after about 15 minutes, after that time, the temperature started to climb back up again because you're absorbing heat from the -8 degrees Celsius environment.
Okay, thank you, Rafil. I hope that answers the question. And the time now is 5:10 p.m. Rafil, could you advise how much more time our attendees can come up with further questions?
Okay.
Oh, we're getting more. Okay. Khaled asks, did you take into account the kinetic effect?
Kinetic effect. Take into account kinetic effect. By kinetic effect, you're talking about like a rho v squared. You're referring to like a rho v squared effect across like nozzles and things like that. I think that's what you might be referring to for this. In this particular case, for the calcs, yes. So that was that was part that effect primarily kinetic energy change. Okay. For kinetic energy change, let's see. No, we did not include. The effect for kinetic energy change in this case. So we're looking primarily at heat transfer and expansion. Yeah. So we didn't. Yeah. So the heat balance in this particular case did not include kinetic energy into the energy balance.
Okay. Thank you, Rafil. If there are no further follow-up on that, let me move on to Incha Azman's question. Azman says, blowdown could prolong more than 15 minutes in some cases. For example, if there are large inventory, high-pressure systems. For discussion's sake, if it goes to some longer time, is it possible that the temperature wall is the lowest, or the wall temperature goes to the lowest fluid temperature? I believe that is the question.
Okay. You see what we see in this case. If you leave the simulation, if you leave this for a very long time, what we're seeing in this particular case, and I think it really depends. It depends on what your temperature gradient is from the ambient down to the fluid. In this particular case, the ambient temperature is hotter than the fluid, so it's about -8. Yeah. So it really depends. It would depend on the following. It depends on what your ambient temperature is, depend on how much metal mass you've got, and depends on the pressure drop and the heat transfer on the fluid side. So it would depend on it pretty much depend on that. So if you were to let this run for a very long time, I don't see why the whole system shouldn't equilibrate at a similar temperature. Because bear in mind that when we started the simulation, we started from a shutdown case, and initially the system, the fuel gas was produced, the fuel gas line was taking in fuel gas. We stopped the simulation and we just did an isochoric settle out. So initially everything came down to the same temperature. So in this case, I guess if you were to blow it down and everything is down to the minimum temperature, and you just leave that at that condition, I'm pretty sure everything would equilibrate to some minimum temperature. particularly if you don't have any active insulation taking place. So I guess why not? Yeah, it's possible. Okay, Yusuf, thanks for coming in. Drop us a line, maybe we can catch up one day.
Yeah, sure,
Thank
will do,
you. Thank you,
Rafil.
so
Catch up later. Okay, bye.
Okay. So I hope, who's asking that question? Azman, I hope that answers your question. Okay, take care, Azman.
thank you, Asman, for attending. Thank you for your support.
Okay. So I guess if there's no, oh, there's here it is.
One last question from Minnie. Does the simulation predict the low temperature profile approaching minimum fluid temperature at nozzle area of vessels where velocity increases due to the nozzle?
I think in this case, if you take a look at this picture over here, we saw the temperature drop a lot in the heat exchanger here. So I think, yeah, that low, and you'll see it happening. This is on the fluid side. So you have like a larger pressure drop or so across your nozzle. So you see this happening over here, because if you take a look at the rest of the equipment, let's see, where's the picture? Here. Yeah, you essentially see nozzles happening around here on the exchanger. Everything else is piping. So I suspect, yeah, we did model this as per the design sheet. So essentially what the simulation is going to do is it's just going to look at the pressure drop. So given that pressure drop that it gets, so if you have a nozzle is going to introduce a nozzle pressure drop. So it's going to calculate the temperature reduction based on the Joule-Thomson effect across that pressure drop. So it would, in this case. Yeah.
Okay. Thank you for the question, Minnie. And I hope that was, yeah. All right. You're welcome, Minnie.
Okay, Pat.
Cooking duties.
Thanks for joining us, Pat. Take care.
Thank you, Pat.
Okay, I think that's all the questions for now.
If anybody thinks of anything that later on they would like answered, please feel free to send that email or send that question to sales@east101.com. And for our prize winners, we might have your email, we might not, we'll have to check. Just to be safe, send us an email anyway. All right, so we can make sure you get your gift. Anything else, Rafil?
I think we're good. I just want to thank everyone for dialing in, for logging in. Appreciate that. I see a lot of old buddies over here, and it's always great to see some old names that I recognize. Hopefully everyone is safe and healthy during these times, and hopefully people are getting some work as well. So everyone take care. Thanks for coming on board, and have a great night.
Thanks, everyone. And we're going to end this webinar.